Okay, in the next couple of videos, what we're going to do is that we're going to take a look at creating some trigonometric functions here, and we're going to then use our graphing calculator or our graphing program to kind of like maximize or minimize anything that we are trying to find based on an angle. And so the first example that I want to talk about is this business of a lifeguard. Okay, so say that you are a lifeguard, and I'm paraphrasing what is written above, and you see somebody over here in the bottom right hand corner, and they are having a rough day. Okay, they are being attacked by a killer goldfish, and so the swimmer, it looks like he's going to be about 120 feet from the shore. Okay, and it says the lifeguard is in a station 300 feet down the beach, which is going to go ahead right from, so this distance right here, okay, to if you were to make a perpendicular line on over to the swimmer. Okay, so that said, something that we want to make sure that is going to be super important to solving this problem, because I did a lot of labeling and whatnot in the diagram, but we want to make sure that we can run, all right, or we know that we can run, and that is going to be 13 feet per second. Okay, and we know that we can swim at 5 feet per second. So how is this going to play into things? And I'm going to show you that in a minute here. So basically, what we want to do is that it asks us some questions, and I want to go after the angle first, because after all, this is a topic in trigonometry. So let's go after the angle, and the angle basically means is that we want to minimize the amount of time it's going to this guy right here. Okay, the person that is going to run down the shoreline here, and then eventually they're going to have to jump into the water to save that person. Okay, and that's going to make a triangle of sort. And so what we got to do is that we got to take it into consideration that they can run faster than they can swim. So if the person just dove right in like that, that would go pretty slow because they can only reach at 5 feet per second, or they can only swim at 5 feet per second. And they don't want to go all the way down, right? Because we're going extra time that they could be diving into the water. Wouldn't want to go all the way perpendicular to the person and then dive in, because you would be running for too long. So basically it's looking at, well, what is the sweet spot that you're going to run down the shore and dive in at some particular angle to save that person using the least amount of time. And what we want to do is that we want to build this function in terms of time, in terms of theta, okay? And we want to minimize that out. So let's go ahead and put some pieces together and get to work. Okay, so to do this out, what we're going to do is we want to label some parts here. And what I want to do, and I'm going to put all the new stuff here in green, is that I want to go after this distance right here, okay? Or I shouldn't say go after, but name that X, okay? And so that means is that this right here, when he's, or she, is going to be running towards the person that is having a hard time with the killer goldfish, this distance right here is going to be 300 minus X. And then, because the total distance right here is 300, okay? So that said, is that at some point they're going to want to dive in and travel this distance. So what we want to do is that we want to find the hypotenuse there, the length of the hypotenuse in terms of X, so we can start to knock that thing out. So let's go ahead and apply the Pythagorean theorem. It seems like it's the most might be the most reasonable way to go. Okay, so the Pythagorean theorem, looking at what I wrote here, basically is going to, we wanted to find, I just labeled that distance d, and it's going to equal the square root of the sum of the square of those sides, just like the Pythagorean theorem would work. Okay, so that said, is that we can start putting the pieces together, and to do so, one of the things that we also have to understand is that we're trying to minimize time. And so with time, we're going to go ahead and have to go distance equals rate times time, because right now we're just dealing with distances and we have some rates right here. So if I want time, I'm going to go ahead and have to divide through by the rate, and that's going to give me time equals a distance divided by a rate. Okay, so let's see how this plays out. Okay, so let's start in a very straightforward format. Okay, is that I want these two parts right here. So the time it's going to take this person is to run down the shore and go from here and here, okay, because that's what we're trying to minimize, is that we know that 300 minus x is a distance, okay, that's in feet. So I got 300 minus x, and how fast can I run as a rate? That's going to be 13 feet, right, per second. So this is going to give me time, because this is the distance and this is the rate, and that's going to kick out a time. Now, we know that the person also has to travel this distance right here, and so that distance divided by a rate, so let's go ahead and put the distance up there. So we got the square root of the sum of 120 squared plus x squared all over this business of 5, because that's how fast the person could swim. Okay, so that is going to be time with respect to x. However, what we want is time with respect to theta. So now what we're going to do is that we're going to concentrate on creating, trying to get x in terms of theta, so we can turn all those x's into thetas and then find out which angle is going to give us the best results in the quickest time to get into our poor guy that's a person that is being snarfed up by this killer goldfish here. Okay, so concentrating on the triangle right here, we just want to say, all right, well, theta in terms of x, we want to play into theta, we want to go ahead and work in the opposite side, and we want to work in this adjacent side. So I can write, okay, and I'm just going to get rid of that little Pythagorean theorem bit here, and then write the tangent of theta equals 120 over x. Okay, so in this case, it looks like then I would have x equals 120 divided by the tangent of theta, and an easier way to write this what can be x equals 120 cotangent theta. Okay, just so we don't have a fraction. So that means is that each one of these x's over here, we could put in a cotangent theta, okay, from here and here. And so we can write a new formula that's going to look like this. Okay, from here you can see that we have the 100 cotangent of theta replaced in for x, and before we turn this over to our graphing calculator, I'm going to do a little bit of simplifying, because in upper level classes you'll have to simplify this down as much as you can in order to make it look very, very nice. So let me I'm going to meet you on a blank page here, and we're going to take a look at simplifying this out before we let our calculator do all the heavy lifting. Okay, so the first thing that I want to do in hopes to simplify this a little bit is take a look at that guy right there. And so I'm going to just work on this part without rewriting everything. So I'm just going to work on that square root part because I think there's some stuff that we could do with it. So is it fair to go ahead and say, that we have the square root of 120 squared plus, and if I'm going to put this into both of those, I can get 120 squared cotangent squared theta. Okay, just like that. Now from there, I can factor out the 120 squared, like that guy. Okay, so the 120 squared comes out of here and here. And so now we have, I believe, an identity here that we have the cotangent squared of theta. So let's look at an identity that's going to help us out with that. And remember, if you forget the identity, we have sine squared plus cosine squared equals 1. And you think about cotangent, you want cotangent to be cosine over sine. So what we can do is that we can divide everything by sine squared, okay, and that's going to give us 1 plus cotangent squared theta equals 1 over sine, so that's going to give me a cosecant squared theta. Okay, so my plan is to take this, okay, this guy right here, and let's replace this in right there. Okay, so let's rewrite. Okay, so there we go. And the nice part of this is that we can get rid of that square root sign then, because remember, there is, anytime that you're taking, say, the square root of two numbers, x and y, you can take the square root of them or move them back and forth through a square root sign if it's over multiplication or division. So therefore, I'm going to take the square root of each one of those separately, like this, and that's going to give me, at the end of the day, something way easier to work with, 120 cosecant theta, okay? And so now let's start to put that back in for this part right here and see where that takes us. Okay, so from here, I'm pretty good with just leaving it, as we don't. We got rid of a lot of the nastiness. We could go ahead and combine those fractions out, and when I say combine them, multiply them, and then add or multiply the bottoms and do the shoelaces here. But I'm going to leave that as is for the time being, and let's go ahead and ask our calculator what is going to be a good graph of this thing, and so we can find out what the minimum angle, or the angle, is going to be to minimize the time. Okay, so here we go. We're going to go ahead and, okay, so this is what the graph looks like of the purple boxed equation above. And so what we're going to do is that we look at this thing, and we have output is going to be time. So this is the seconds right here, and this is going to be the angle in which the lifeguard, is going to dive in. So it looks like that if we put this all together and say that if the lifeguard is going to dive in at an angle of 67.38 degrees, it's going to take 45.231 seconds to get to that person. Okay, now that is super important. However, we have a little bit more to do because we've only covered this part of the question. What angle should you take for the best approach? Okay, so it wants us to also say, given that you want to reach the swimmer quickly as possible, how far down the beach do you run? And how far do you swim? And so it looks like it also wants this distance right here and this distance, okay? And since we have x, okay, we can take this part right here. We know that tangent is going to equal 120 over x, and we know now what theta is, okay? So once we know what theta is, and we know that from the other screen, that was going to be, what, 67, I can't remember, 67.38 degrees, we can easily find out how far down the beach we run and how far we swim just by putting that in, okay? So here we go. Let's find out what x is by plugging that into tangent. So I'm going to get tangent of 67.38 degrees equals 120 over x, okay? And after we manipulate the formula for x, we're going to get x equals 120 divided by tangent 6738 degrees there, and that is going to approximately give us, well, it looks like even if we take it out to many decimal places, it's just going to be 50. Okay, so that's easy for us to work about here. So if we want to know what this distance is right here, we just plug that in. So we got 300 minus 50, which is going to give us, that's 250 feet. Okay, good. And so 250 feet, and now we need to find out how far does the person swim. And so D, we know equals the Pythagorean theorem. We could go ahead and plug that in because we know that x is 50 here. And doing out the Pythagorean theorem, that is going to give us 130 feet. Okay, and so the new stuff that we got that was asking us is going to be right here, the 130 feet and the 250 feet. Okay, so if we were to put that together and say the following, putting all the pieces together, and I'm just going to verbally say this, is that if the lifeguard runs down the beach 250 feet and then dives in at an angle of 67.38 degrees, then swims an additional 130 feet, then they will reach the person that is in distress 45.231 seconds, and that will be the minimum amount. So lots of moving parts to this one, but at the same point, it's a good problem that really puts things, all the pieces together that we've been learning so far. So that's how you do that one, and I'll see you in the next video.